Good morning. The IT gods seem to be smiling on us today. We seem to have actually a computer projector, an iClicker, and the whole ball game working. So these are some iClicker questions that I was going to do on Wednesday, but hopefully they're not too stale. So the first one is about the natural carbon cycle. Is it our friend or our enemy today? Is it helping or hurting climate? Is it keeping climate stable? Is it stabilizing things, or is it making things worse today? Amplifying or moderating? So the panel of experts is spoken, and looks like a consensus is being sort of unofficially negotiated there that the natural carbon cycle today is moderating climate change, and that's the correct answer because the oceans and the land are taking up about half of the CO2 that we're emitting. So if it weren't for them, the atmospheric CO2 concentration would be rising faster than it is. Plants, do they grow better or worse if there's more CO2 in the air? They grow better. Actually, that's true because they have to take up CO2 from the air. The way they do that, we didn't really talk about that, but it's really kind of cool. There are these little vents in the bottoms of leaves that allow gases to go in and out, and they have to be open enough to let CO2 in, but when they open up they lose water. So the more CO2 there is, the less they have to be open, those vents. They're called stomata. And so higher CO2 levels help the plants cope with water stress a little better. Actually, one interesting thing, one of the only things that they can say pretty clearly about how forests do in high CO2 is that poison ivy does much better when there's high CO2 concentrations. I don't know why that is, except just, the general evilness of this whole thing. Just a curiosity. The fossil fuel CO2 that isn't in the atmosphere, where did it go? Is it mostly into the land surface or mostly into the ocean? Or about half and half? So you're coming in strong for B, mostly into the ocean. And that's a good answer if we take the land as a whole. That's a correct answer because there's carbon coming out of the land surface where there's deforestation going on, and then there's carbon going into the land surface that we're calling the missing sink because we don't know where it's going or why. On balance, the land surface is not really doing very much. But if I were sitting here with an iClicker, I would have said about half in each because I sort of divide in my mind the deforestation parts of the land surface from the missing sink parts of the land surface. But, I didn't really... That was just my own kind of thinking, and maybe if you take the land overall, then it's sort of a net wash as far as the land goes. It's not doing much. So the ingredient of seawater that CO2 reacts with, there's sort of an anti-CO2, which is where the CO2 kind of goes to ground. It partners with this other chemical and thereby hides from the atmosphere. And so the existence of this chemical helps seawater to take up more CO2. And that ingredient, there you go, carbonate ion. Carbonate ion, so CO2 is sort of an acid-base species. Carbonic acid is what CO2 turns into in water if you just react it with a water, and that's an acid. Bicarbonate is sort of a neutral compound, and then carbonate is a base, and the base reacts with the CO2 acid. So I don't know if any of you ever saw the movie Apollo 13 with Tom Hanks, but when he's out there in this little spacecraft and they're going to run out of air. The particular problem was that the CO2 levels in that thing were going to get too high. So at one point, I remember the crew cut guy on the ground who's sort of running things, dumps a whole bunch of stuff on the table, and they had to figure out how to run the air in this thing. This is all stuff that they had up in the spaceship. They had to figure out how to run air through this thing through a canister of some sort of a base. because base reacts with CO2 and sort of scrubs it. This is how they would scrub CO2 out of smokestacks, by reacting it with a base. They do it in submarines and things like that now. So if you're ever trapped in a submarine and you've got a can of Drano and you're about to die from too much CO2, you know what to do now. You just run the air through the Drano, which is base, sodium hydroxide, and it will scrub the CO2 right out of it. So that's what the carbonate ion is. It's like base, chemical base. As the amount of CO2 dissolved in seawater increases, the amount of the anti-CO2 carbonate ion, does it increase or decrease or stay the same? It decreases. That's right. And so, you know, the intuition here would lead you astray, because you would think, you know, you put more carbon in and there's going to be more of all different kinds of carbon, like you know, a rising tide floats all boats. But actually what happens is this carbonate ion gets consumed because it reacts with CO2. So by extension, calcium carbonate, like limestone, you might think would be where CO2 would go to in the ocean, you know, if you put more CO2 in, because the rising tide would float all boats. And so it, you know, limestone, calcium carbonate has carbon in it. So, you know, you would think that would be a good place to put carbon that you know, when you put more CO2 in. But actually putting CO2 in, because CO2 is an acid and calcium carbonate is a solid form of this base, and it tends to dissolve in response to the CO2, your intuition it leads you astray. The rising tide doesn't float all boats. CO2, the acid form, goes up. Carbonate or calcium carbonate, the base form, goes down. So the decrease in carbonate ion makes seawater a stronger buffer for taking up more CO2, or a weaker buffer, or does it not really make any difference? Really? All right, the forces of good are holding on here just tenuously. Yeah, so carbonate ion, because it reacts with CO2, the anti-CO2, when you have less of it, then there's less capacity to hide more CO2 in the seawater. So, you know, it's like the canister of base in Apollo 13. Once it starts getting used up, because all the CO2 has gone in there, that canister of base is not as good at pulling more CO2 out of the air. So that sort of does make sense. Okay. So where we are in the class, conceptually, I mean, where we are sort of in our thinking about this whole thing, you know a lot about the physics of climate and how it is that, in principle, blocking outgoing energy by putting more CO2 in the air could make the Earth warmer. But you also know that the models are, there are parts of the climate system that are very important, like clouds. Cloud droplets in particular is a really important part of the climate, which can't really be predicted very well from first principles, because the physics is just too complicated, and it goes all the way from stuff that happens on a scale of micrometers as little droplets coalesce, you know, all the way up to the whole planet. And you just can't sort of start from Newton's laws of motion and design a whole model that predicts everything. And so the models say that putting CO2 into the air should cause significant warming, but the models, you know, it's not really enough on its own, a model result like that, to you know, really convince anybody that there's a problem. So, I mean, not if it takes, you know, money to avoid the problem. So what you look for in such a case is what's called a smoking gun. Some sort of proof from the real world that humans are warming climate. And the basic phenomenon that we're interested in is the temperature of the Earth. I mean, there's droughts and there's, hurricanes and other sorts of things that you've read about in 6 degrees and all that. But the primary phenomenon involves the energy, the heat energy. And so is the world warming? That's sort of the question. And it's not such a trivial question to answer, actually, because there's a lot of weather, and the temperature at any given place, varies quite a bit from day to day and week to week and day to night and things like that. And so getting the average temperature of the Earth and getting it, a good enough, representation of the average temperature of the Earth that you can tell if it's changing through time is not really such a trivial thing to do. So the thermometer was invented in the year 1714 by Fahrenheit. And he came up with his Fahrenheit temperature scale, which one story I heard about where this temperature scale came from is that what he chose for 100 was his body temperature, which now we say 98.6, but it's not so bad. And then 0 degrees was the coldest that he ever saw in the course of the first winter that he had his new toy thermometer. So he just said, okay, he put the lines on his thing, and that's the temperature scale. And it wasn't too much, it was just, in about the same years, just a few years after, that Celsius came up with the centigrade scale, which is kind of a, it makes a little more sense. It has 0 degrees at the freezing point of water and 100 degrees at the boiling point of water. And the freezing and boiling points of water, or some other chemical too, but water, is everywhere, make a really, really good way of calibrating thermometers. So, there are people who were trying to measure the CO2 concentration in the air 100 or more years ago, and that's kind of dicey, and we have their data, what they wrote down, but it's hard to know what it means because, a measurement like that is hard, and there's not some real simple way to, calibrate the instrument for CO2 concentrations. But for temperature, it's pretty easy because water at 1 atmosphere, at 1 atmosphere surface pressure, as long as you're not up in the mountains someplace, always boils and freezes at the same temperatures. And so the temperature measurements that we have going back pretty far back are pretty reliable compared to some of the other sorts of scientific measurements that had been made early on. And a lot of people have been interested in knowing what the weather is going to be and what the temperatures are, just because, do you put on a coat or not, for a long time. So there's more than just the scientific interest. There's also kind of a practical interest, which fuels lots of these thermometers to be, deployed all over the place at weather stations and people to make records of temperatures and things like that. So compared to some of the other kinds of information that we would like from the past, the temperatures are sort of well documented. Now there's sort of two different domains of temperatures that we would like to know. There's the air temperature on land. The air temperature is over land. That's different, strictly speaking, from the temperature, at the ground itself. If you stuck a thermometer on the sidewalk, you might find a very different temperature than if you wave it around just above the sidewalk. In the ocean, the sea surface temperature is very close to the air temperature, and there are measurements of sea surface temperature that go back pretty far too. So now ultimately, we want to take a whole bunch of the land measurements and a whole bunch of the ocean measurements and, say that they are irregularly spaced in space. So you got a lot of weather stations on this island, and then not too much, in this giant forest or something like that. You don't want to just take the average of all these numbers. You want to sort of weight them so that this average temperature over some big area and this average temperature over a smaller area. You want to sort of grid the temperatures or somehow weight them so that you get the average for the whole area instead of just the average of all of the numbers. So you weight them. If there's only one measurement in this big area, it gets more weight in your analysis. But there's also the potential for biases in putting together an average temperature of the Earth that you have to be real careful of. So we're going to, and there's sort of different problems between the land and the ocean. So we'll start with the land first and talk about that quickly, and then go on to the oceans. So the potential problem with land temperatures is a phenomenon, a real phenomenon called the urban heat island effect. So if you have land that has lots of grass on it, vegetation or something, and the sunlight comes and it's dumping heat into that land, a lot of that heat gets carried away as, maybe I don't want to draw that as a wiggly line because we use that for infrared, gets carried away as water vapor. Because you know that when you evaporate water, it takes heat to do that. So each molecule of water vapor is carrying some amount of heat. That's the latent heat. So that's the stuff you stick your hand in the tea kettle and you burn yourself with. It's very real heat. Whereas if you have some kind of a paved, urban jungle kind of thing, a sidewalk or a street, and then the heat comes in from the sunlight, it gets carried away by infrared. And to get rid of that heat, you got to have a high enough temperature so that sigma t to the fourth is high enough to carry away the heat. So the bottom line is that a rural or vegetated kind of a landscape is going to be cooler in general than a paved one. So this is, Mayor Daley's shtick about green roofs. He's got a green roof on top of downtown. Maybe you can take a tour of it someday. It's kind of, I don't know, it's just a big bunch of grass basically, but it makes a huge difference to the heating of City Hall, and they've got, they've got it over the city part and not over the state part. So Blagojevich was roasting in his side, and Daley was nice and cool on his side, I guess. So the question is whether, let's say you had some weather station and it was in a very kind of rural place originally, maybe 100 years ago, but it got grown up and urbanized over that time. So you might see the temperature of that site warming up, but it's not due to global warming, and it's not, hot urban areas do contribute something to the average temperature of the Earth, but the question is whether the thermometer record might, have too much urban stuff in it, so it is biased and shows more warming than the average of the temperature of the Earth actually does. It doesn't seem as though this turns out to be a big problem. So I can show you, these are a whole bunch of temperature reconstructions. So the average temperature of the Earth relative to some zero that is from 1950 or something like that. And these reconstructions go all the way back to 1881. So the purple one there comes from a paper that was published in 1881. So there's no data in purple that goes beyond then, because that was the future at the time. There's this one kind of weirdo outlier here, published in 1950, but after that, basically all of these different studies are right on top of each other, and they've done, what they do is you look through all this air temperature data, and you get rid of data points that you think might have been affected by the urban heat island effect. And what the bottom line is, it doesn't seem to make any difference, which stations you throw out. The number is sort of robust in either case. So, to me, I look at this and I see just incredible agreement. Others may look at it and see some sort of a conspiracy or a herd kind of an effect. The story that you can hear is that it's easier to get your grants funded if you're not challenging anybody, so you go along with the herd, and that science has this tendency to sort of find consensus artificially. And I don't really believe that's true, because the way to get famous as a scientist is to knock over the apple cart. If there's some huge body of science and it's all wrong and I figure it out, I get to be a big shot by knocking that over. So, if there was something and it wasn't warming up at the end there and it was just some stupid mistake that everybody else was too stupid to see before me and I found it, I would publish it in a minute. And it's true that an extraordinary claim like that requires extraordinary proof, but that's what we do, is we fight battles, and it's like a free marketplace of ideas. It's a dog-eat-dog sort of world. And consensus, it might be easier to get a grant funded if you write a boring grant proposal, maybe, or maybe not. Certainly maybe easier to get a paper funded if it doesn't challenge anything. But it's not the way, science works. You get all kinds of ridiculous challenges to things that don't really survive, because in the end, the real picture, they had it right the first time. And that's cool. That sort of keeps everything strong and makes sure that you don't have this sort of herd thing. So, scientists are like cats. They don't really. I don't think they herd like this. All right. So there are also sea surface temperatures. And here, there is a potential bias that actually did turn out to be important and had to be corrected for. Historically, there are two ways that people on ships out at sea measured the temperature of water. One way is with a bucket. So you got a bucket on a rope, and you throw it into the water, and you pull up a thing of water, and you stick a thermometer in it and see what it says. Well, the thing about a bucket is that there's water sort of dripping on the sides, and it's evaporating. And as it evaporates, it takes heat away, because water vapor carries this latent heat again. So the temperatures that they get from this tended to be biased a little bit toward the cold side. The other way to measure temperatures of surface water is with the engine cooling water. So to keep motors on boats cool, they pull in some water from the surface, of what they're floating in, and it goes through the heat exchangers and then gets dumped out. But before it goes to the engine and gets heated up, there's a thermometer there that measures and records these temperatures. And it's important for the engineers, the guys down in the engine room, because how warm or cold the water is coming in determines how their engine is going to be running. So they pay attention to this. So this bucket tended to be sort of biased cold a bit relative to the engine water. So you want the air temperatures and the ocean temperatures to sort of be consistent with each other. You want them to be telling the same story. But because the temperatures on land are different in principle from the temperatures in the ocean, you can't just sort of compare them directly, because the ocean has an infinite amount of water to evaporate away, and it's also got a lot of heat stored in the water. So you shine sun on the ocean, and it doesn't necessarily warm the air up as much as it would over a parking lot. So it's kind of like the urban heat island effect, only instead of grass, you're talking about ocean. So what they do is they they have temperatures in the ocean, and then they impose those in a model. So they've got this climate model, and the temperature of the surface ocean at every grid point in that climate model comes from one of these gridded ocean temperature kind of reconstructions. And so that temperature then sort of drives the air temperature in the ocean, and then that drives, to some extent, the air temperature on land. So you get this air temperature from a model, and then you compare that with observed air temperature. You know, are they the same or not? So the figure here, it has a couple of different lines on it. Not really so easy to tell the difference, but this dashed line here that suddenly pops up right at the end of the Second World War is the ocean temperatures that are not corrected for the switch over from they used to do buckets to they started to do the engine intake method. So I don't really know much about this. Is not my field, but it's amazing to me that the big correction in sea surface temperatures is right there at 1945 or 46. Somehow, all of a sudden, you know, there was this change after the war in how they did this. So then the corrected ocean temperatures are here. Let's see. No, actually, these are all air temperatures, but these air temperatures are from the uncorrected ocean temperatures, and then the corrected ocean temperatures are the dashed line there, and then the real air temperatures that they're comparing to is a solid line here. And so what they find is that that this works just fine. So the ocean temperatures and the air temperatures seem like they're telling us the same thing. They've got different potential problems, but you know, if they're giving us the same answer, then you know that lends some credibility that they're actually, you know, not like wrong in some horrible way. Then there's another way to measure temperature of the Earth, and that is by satellites. There is a particular kind of sensor aboard a fleet of satellites called the microwave sounding unit. Or MSU. And it uses microwave light from oxygen in the air. And the hotter the oxygen is, the more intense this light is. So this is a lot like the black body radiation that comes from a greenhouse gas. This is at much longer wavelength. Microwaves are much longer than infrared. And oxygen, O2, is not a greenhouse gas, so it's not really making, you know, much light. But something about the way that the electrons are in that, I don't really understand myself, generates these microwaves. And the more intense, the hotter it is, the more intense these microwaves are. And now for a long time, these satellites didn't seem to be showing the same sort of warming as the ground temperatures were. So you could read in the Wall Street Journal or someplace like that from George Will, my favorite commentator on the wrong side of things, that the Earth isn't warming. The satellites prove it. And satellites, you know, a satellite is an expensive thing, and so, you know, you sort of trust implicitly something like that rather than a bunch of thermometers from a bunch of people all over the place. But it turned out there were some issues, and the satellites, the temperature trend from satellites have been sort of, you know, that they've been debugged, and they now show pretty much the same thing as all the other temperature records. The problems had to do with decay of the orbit affects the signal. And it's actually multiple satellites. It's not just a single one, and so they all have to be calibrated to each other, because you put up a new one and you don't know, I mean, that you're getting, I mean, you need to relate one to the other, so they have to be sort of calibrated to each other. And then the really big effect turned out to be the response from temperatures at different altitudes. So the ground and the air, right above the ground is what they measure with thermometers, and the thermometers say that that's getting warmer. But actually, the stratosphere is getting cooler, and that's because when you put more CO2 into the stratosphere, what the CO2 does is it shoots away heat. It's like putting a bunch of cooling fins kind of up in the stratosphere, a way for heat to go away. And so it's predicted and observed that there's cooling up in the upper atmosphere. And so for a long time, the warming, looking down through the whole atmosphere column from the surface, the warming from the lower atmosphere was being sort of masked by cooling in the upper atmosphere. So we have the instrumental record, that's the thermometers, and then we have this satellites, which haven't been flying since the 1700s, just more recently, and they're a lot sort of spikier. Whether that's real or not, I don't know, but the general trend is sort of the same. So again, it's sort of confirming everything is kind of falling into place, that the Earth is getting warmer. Then the question is this caused by people, or is it just sort of natural variation? If you were going to make a T-shirt for this class and choose very iconic images to put on the front of it, one of them would probably be the Mauna Loa CO2 curve going up. And this one might be another one. This one shows the change in the radiative forcing, so the watts per square meter of energy balance, resulting from various natural and artificial changes since 1950 or something like that. And so the scale is down at the bottom. It's watts per square meter. You guys know all about watts per square meter. And the big forcer on the warming side is carbon dioxide, which is putting in about 1.5 watts per square meter of energy. So that's like a little, Christmas tree light bulb or something is about a watt or two, something like that. So it's like one of those little Christmas tree light bulbs. Every square meter of this over the whole planet is that. So CO2 is the biggest forcing, the biggest thing that's causing there to be warming. And you see other greenhouse gases just below that. There's methane, which, molecule per molecule is more powerful than CO2, but there haven't been as many molecules changed. N2O is laughing gas. It has a lifetime of about 150 years in the atmosphere. It mostly comes from agriculture. In fact, the latest IPCC report blamed Brazil. Brazil was responsible because of, I don't know why, because it's tropical and they do agriculture there with fertilizers. It surprised me, actually. Brazil is responsible for like more than half of the N2O emissions globally. And then halocarbons is the yellow thing, so that's freons and other chemicals that are so band undersaturated that a molecule of one of those might be worth 10,000 molecules of CO2, but there are much fewer molecules of them, so the net effect is, whatever that is, less than 1/2 watt per square meter. And then there are aerosols that we talked about that tend to cool the planet. So the direct effect, again, is how the haze itself scatters sunlight back to space. And then the indirect effect is changing the cloud droplet size. And so you see that the indirect effect is bigger even than the direct effect. But the uncertainties here are huge. You know, the uncertainties on the warming side are much smaller than the uncertainties on the cooling side. And the implication of that is that if it turns out that the real effect from the aerosols is big, like this, then that means that the Earth has warmed as much as it has with a smaller sort of overall forcing. So if the aerosols have been keeping us particularly cool, that's kind of bad news because, you know, if we clean up the coal power plants and don't have aerosols anymore, that means that that means that we'd be eliminating a huge cooling force, and you know, then we got sort of more warming. So the uncertainty in the cooling forcing there is kind of an important thing because it sort of speaks to the uncertainty in the overall climate system. And now there's this other forcing here, solar irradiance, a natural climate forcing. So the sun gets hotter and cooler on a sort of 11-year sunspot cycle. It's not a huge effect, but it's measurable and real. But what did I do with my chalk? There it is. The sunspot cycle has this sort of 11-year period. And when there are more sunspots, the sun is hotter. So we could either put sunspots on this vertical axis, or we could say solar intensity. And it's not a huge effect, but it is real. However, since sort of 1950 to today, there have been a bunch of these, you know, several of these cycles, and the overall trend is not very much trend. So you can see that the forcing from the solar irradiance is pretty tiny compared to these other things. So then what you do is you take all the climate models that have been developed around the world. This is what IPCC did. They said, all the research groups that have these climate models, we want to see two sets of experiments. One set has all the things that drive the climate as they have changed since, you know, the beginning of the century. And then the other set has just the natural forcings. So this is a figure from the IPCC report. It shows, well, there's the global temperature. The temperature of the whole globe is down in this panel. So we're starting from, you know, a little bit after the beginning of the last century and going to, you know, sort of the year 2000 or something. And the measurements from the thermometers are the solid black line in these various plots. So here's the land only and the ocean. So you can see that the land is warmed more than the ocean has, and that's because the ocean has all this water vapor to carry away heat, and the land doesn't have as much. So it makes sense that land should warm more. And then these plots up here are for different parts, different continental areas. And so we can kind of see that in the high latitudes, there's been sort of more warming maybe than in the low latitudes. So that's this high latitude amplification, which is mostly caused by the ice albedo feedback. So ice melts and it makes That's a positive feedback that warms things up even more than if it hadn't melted. And where you have ice is mostly in the high latitudes. So the climate changes are thought to be and found to be more intense in the high latitudes. Okay, so those are the solid black lines. Then the kind of areas, these sort of colored areas in the plots are the model results. So the salmon color are the natural plus human, and then the blue blobs are the models when they were only told about the natural climate forcings. And so there are 20 models, I think, thereabouts, 21, 19, something like that, from around the world, all sort of competing with each other, you know, trying to be the best. And then all of these model results are archived now with the IPCC. So there's a lot of research going on, just people downloading the results from 20 different models and kind of looking at them all to kind of see, you know, which ones do best at what ways and which ones have which mechanisms in them and things like that. So the bottom line, though, the sort of really simple result is that the models, when you tell them about the greenhouse gases, they get the warming. And if you don't tell them about the greenhouse gases changing, they don't. So that seems to indicate that this warming, since about 1970, is our smoking gun. We can explain it with CO2, but we can't explain it without CO2. Sort of as simple as that, really. Now, you may wonder, you might challenge this and say, but you know, there's all kinds of complicated stuff in the climate system, stuff that you can't really get your hands on very well, like the cloud droplet size. That was a huge effect. So, you know, how can you say for sure that it's greenhouse gases like CO2 when you can't, you know, be ever certain about anything in the climate system because it's so complicated that you can't, you know, capture it totally inside a climate model. So there's a climate skeptic guy at MIT named Richard Lindzen, and the way he put it with some sort of derisiveness was that climate modelers are just not smart enough to think about or to think of any other explanation. They just call it greenhouse gases because we can't think of anything else to explain it. But the way I think about this is by analogy to sort of a detective story. So say you're a detective and the case that you're working on, the butler was found standing there with a smoking gun in his hand, and there's the dead guy on the ground. And so, you know, at first glance, it looks like a slam dunk that this is, you know, he's the guy who did it. But your partner is kind of like real skeptical, and he's challenging you and sort of poking you. And it's also a real high-profile case, so you have to check out everything. You know, it's not just sort of your generic, you know, lowlife in a gutter someplace. It's somebody important, so the press is after you. And so you got to check out everything. You check out the gun belonged to the butler and had his fingerprints on it, been fired, same bullet, all that stuff sort of checks out. But your partner, this contrary cuss kind of a guy, says, well, you're just not smart enough. I think the chauffeur did it maybe, not the butler. And you're just not smart enough to think about how the chauffeur could have possibly done it. And you know, you check it out, and it's not obvious how he could have because he wasn't there. He was at you know, someplace else. He's got an alibi. He was at his sister's wedding in Kentucky or something like that. But still, it's impossible to really prove a negative, to prove that the chauffeur didn't do it. But if your partner wants to drag the chauffeur into court and convict him, he's got to convince the jury, got to explain to the jury what the butler was doing with the smoking gun in his hand. If you're going to convict the chauffeur, you got to unconvict the butler. So, you know, translating back out of the analogy, there's a perfectly good explanation for the warming given the greenhouse gases. And if you want to say, well, really, the climate doesn't care about greenhouse gases and, you know, it was just natural variability, you got to explain why the CO2 wouldn't be causing the warming first, and then you got to explain what it is that is causing the warming second. And so it's like two things you got to ask for, not just one, but two things, two impossible things or difficult things. And so far there aren't any explanations that do that. There's no sort of credible hypothesis or theory or model that would predict that the climate won't change if we keep putting CO2 into the atmosphere. All of the IPCC models show that warming. There's no sort of dissension on that front. So that's the smoking gun. So I will see you on Monday.